In this video, we are going to demonstrate how to do a preliminary hydraulic design of the Riffle trapezoidal cross-section. So a Rosgan C4 channel carries a bankful flow rate of 300 cubic feet per second. The average bankful slope is 0.006. Determine the preliminary hydraulic design of the Riffle. From that reference from Harman and Starr, we can get design parameters for a C4 channel. The Riffle bankful top width divided by the Riffle mean depth is in the range from 10 to 15. The sinuosity is in the range from 1.2 to 1.4, and the valley slope is equal to 0.005 to 0.015. The friction slope of the Riffle divided by the overall bankful friction slope is 1.2 to 1.5. This means the slope of the water surface going through the Riffle will be about 1.2 to 1.5 greater than the 0.006, which is the overall average bankful slope. As you can see, this is the input in a lingo file where all of the variables have been defined. So you can see there's BTW, bankful top width, BMD, bankful mean depth, and then BTW underscore BMD. That's the bankful top width to bankful mean depth ratio. And as you continue to look down the list, you can see all of these should be fairly familiar to you in terms of the variables. The one new one might be the Darcy-Weisbach friction factor, which you probably haven't used since hydraulic engineering when you were doing pipe flow. But you can see we have U star, the Riffle shear velocity, which was discussed in sediment transport. U, the Riffle average velocity. We're going to calculate the bottom width of the Riffle two different ways to ensure that our results are accurate. So you notice we have BA, Riffle bottom width determined by the area, BT, Riffle bottom width determined by the top width. So those will be evaluated using two different equations. This is an iterative process. We're given a bankful flow rate, and the Riffle that we size will have the design flow rate, and we will compare these two to see if the Riffle that we are designing can handle the bankful flow rate. What you're given here, or you will select as design parameters, the bankful top width underscore bankful mean depth. This is characteristic of the C4 channel, and as you recall, it was anywhere from 10 to 15. So I'm going to select the design parameter of 14. This is given, determined from the survey, the average water surface slope. Sinuosity of 1.3 would be within the design parameters of the C4 channel. And the bankful flow rate was 300. That would have been determined from the hydrologic analysis. So now the next three lines, we're going to estimate the bankful top width of the trapezoidal section. I'm going to select the side slope of 2.1 as my design parameter. And the friction slope of the Riffle I'm going to assume is 30% greater than the overall average water surface slope. So this is the list of the calculations. And as you have seen numerous times during this semester, I very much define everything that I'm talking about in terms of calculations. So I can look back and I know exactly what each line is doing. So you can see we start by determining the bankful mean depth, and then cross-sectional area, bankful flow depth. You can see the area of the trapezoid. Then I calculate the bankful bottom width using two different equations. the wetted perimeter, hydraulic radius, friction slope through the riffle. This is when it takes the overall average slope and increases it by 30%. Compute the velocity, taking the bank full flow divided by the cross-sectional area. Shear velocity. Compute the ratio of U over U star. That allows the computation of the Darcy-Weisbach friction factor. And then, using the friction factor, I'm going to calculate Manning's N. And then, using Jarrett's equation, I'm also going to calculate Manning's N, just to ensure that the two of those are close together. Finally, after I've sized this, I'm going to compute what this riffle cross-section will carry and calculate the Froude number at the normal depth to ensure that it's subcritical flow. These are the results from the Lingo simulation. The left-hand side contains a list of the knowns. The right-hand side contains a list that was calculated. So you can see by selecting a top width of 33 feet with the 2-to-1 side slopes, I get a cross-sectional area, depth of flow in the riffle. The bottom width computed two different ways, so you can see those equations agree. Wetted perimeter, hydraulic radius. There's the slope of the valley, shows up twice. Average velocity, 3.86 feet per second. U star, 0.76 feet per second. U over U star gives me a ratio of 5.1, a Darcy-Weisbach friction factor of 0.31. And then you see Manning's roughness coefficient calculated by two different means. We have 0.58, 0.59, and 0.54. That's very close. And for this size riffle, it would have a design capacity of 326.66 cubic feet per second. Now that's more than 300. And your first tendency, especially after taking a lot of structural engineering classes, would be to actually accept that larger value. In natural channel design, that may not always be a good decision, because that may be denying the flow which is above bankful may not be able to reach out into the floodplains. And so putting a larger size cross-section actually might entrench the channel more. So it's not always a good decision to simply be conservative.